Once the model, once the model's algorithms successfully identify objects, the computer can output a decision or an outcome using computer vision, natural language processing, name entity resolution, or other computer processes. Here's another good definition for data labeling. It transforms raw, unstructured data into structured data based on ontology or classification system. That is appropriate for the machine learning model. For example, security cameras provide enormous volumes of unstructured video data. Data labeling can transform this raw data into structured data by identifying objects such as persons and shopping items. Then the relationships and events that apply to those objects. With this structure applied, the data can be used to train a theft detection model, for example. To give you an idea of what data sets are used to train machine learning, for example, a training data set, as you can see, as the top stack there in the diagram, is the initial data set that teaches machine learning models to identify desired patterns or perform a particular task. A testing data set is used to evaluate how effective the training was or how accurate the model is. Both the training data and test data are usually labeled for supervised learning. And then there's validation data that checks the results of the learning process and helps protect models from overfitting and underfitting. From my understanding, validation data doesn't need to be labeled usually. Types of data labeling. So you have natural language processing, audio processing, and the big one, and I think the newest kind of development is computer vision. So natural language processing usually entails manually identifying important sections of a text or tag the text with specific labels to generate your training data set. For example, identifying the sentiment or intent of a text blurb, identifying parts of speech, classifying proper nouns like places and people, and identifying text and images, PDFs or other files. To do that, you can draw a bounding box around text and manually transcribe, annotate the text in your training data set. Natural language processing models are used for sentiment analysis, entity name recognition, and optical character recognition. Audio processing, on the other hand, converts all kinds of sounds such as speech, wildlife noises, like barks, whistles, or chirps, and building sounds, breaking glass, scans, or alarms, into a structured format so it can be used in machine learning. Audio processing usually entails first manually transcribing it into written text. From there, you can uncover deeper information about the audio by adding tags and categorizing the audio. This categorized audio then becomes your training data set. But today we're going to focus, as I mentioned, on computer vision, which is where there's a lot of demand for today. Computer vision is a field of artificial intelligence that trains computers to interpret and understand the visual world. Using digital images from cameras and videos and deep learning models, machines can accurately identify and classify objects, and then react to what they see. That was a definition from SAS.com. Early experiments in computer vision took place in the 1950s, using some of the first neural networks to detect the edges of an object and to sort simple objects into categories like circles and squares. In the 1970s, the first commercial use of computer vision interpreted typed or handwritten text using optical character recognition. This advancement was used to interpret written text for the blind. As the internet matured in the 1990s, making large sets of images available online for analysis, facial recognition programs flourished. These growing data sets helped make it possible for machines to identify specific people in photos and videos. Today, a number of factors have converged to bring about a renaissance in computer vision. Mobile technology with built-in cameras has saturated the world with photos and videos. Computing power has become more affordable and easily accessible. Hardware designed for computer vision and analysis is more widely available. New algorithms like convolutional neural networks can take advantage of the hardware and software capabilities. The effects of these advances on the computer vision field have been astounding. Accuracy rates for object identification and classification have gone from 50% to 99% in less than a decade. And today's systems are more accurate than humans at quickly detecting and reacting to visual inputs. I'm not sure about that last part, but I'm quoting from the SAS.com. But they're claiming that now systems are more accurate than humans at quickly detecting, reacting to visual stuff. So here are some examples of computer vision applications. So facial recognition. This particular image here has a labeled facial image that has 95 points. Human pose tracking or human pose estimations. The most popular applications are human activity estimation, motion transfer and augmented reality for our VR folks, training robots, motion tracking for consoles or video games, and human fall detection. Object detection. So, we talked about bounding boxes earlier. So if you just put a bounding box around an object, then you've successfully classified that. But if you actually put a box around just that exact object in that picture, then you've localized it as well and put those two together. And if the algorithm is able to actually segment certain objects and tell them from apart from each other, then you have object detection. This is one thing that we do almost every day that actually is a form of data labeling that people are partaking in unknowingly. But human verification process when logging into your accounts is another good example of object classification or image recognition. You're basically doing some data annotation for Google without knowing it, and you're helping them teach their machine learning by doing these. So as millions of users identify hard to read text and pick out objects in blurry images, that data is fed into AI computer programs so that they become better at those tasks as well. What are the different types of data labeling methods? So when building a computer vision system, you first need to label images, or you can get more granular and actually label pixels or key points. Or you can create a border, a bounding box like we discussed earlier, that fully encloses a digital image, such as a bounding box, to generate your training data set. So for example, you can classify images by quality type, like product versus lifestyle images, or content, what's actually in the image itself, or you can segment an image at the pixel level. Some examples, other examples of data labeling methods are point, bounding box, polygon, cuboid, scribbles, and superpixels. So bounding boxes are good enough for some quick object detection, but if you need something that's a little bit more precise, polygon tools allows for finer segmentation of the object from the background. But doing it that way would be a lot more time consuming. So sometimes some of the more advanced annotation companies would use smart tools that can group pixels or colors and shades, group pixels of like colors, say similar shades and things like that, so that a human annotator can segment objects a lot faster. Basically, they could just hover over the item, click on a few of those super pixels, and make the data annotation a lot faster and a lot more streamlined. But just to show you what that looks like, here is a demo from Alegion of what a smart poly is.
Allegion's enhanced Smart Poly makes segmentation tasks easier and faster than ever. This latest release features several key enhancements. A new machine learning model provides more accurate segmentation for a wider variety of objects. Polygon proposals are now generated with a single click in the region of interest. Interactive gestures enable quick and accurate polygon refinement. Click inside and outside the polygon to include or exclude specific regions of the image. Adjust the prediction confidence threshold to globally adjust the segmented region. Put it all together, and Smart Poly can be many times faster than manual segmentation. Try it for your next segmentation project. Smart Poly is featured in Alegion Control for both image and video segmentation.
Okay, so that was one of my shameless plugs there. Promise it's my last one. So that brings us to humans in the loop, or the concept of machines and humans working together. Because as I described earlier, data labeling is so time consuming and it gets very expensive, and hours kind of stack up real quickly when you're having to annotate, especially videos where there's hundreds of seconds of a clip, right? So hundreds of images to annotate. So as with any project management efforts, data labeling is often a balance between time, quality, and price. You rely too much on the machine learning to label your data, and you decrease your time and price, but the quality or accuracy may go down along with that. Rely too heavily on the humans to annotate, and you would increase the quality, but also the time, and ultimately the cost would go up as well. So in a nutshell, humans in the loop machine human in the loop machine learning relies on human feedback to improve the quality of the data used to train machine learning models. And so as you can see in this diagram, if let's say there was an unambiguous data set sent to a human labeler for annotation, that human annotator can then go in and fix a few things. That way, that feeds actually some data into the machine learning, making it a lot more efficient in the future. So it becomes like a feedback loop where humans are helping the machines annotate and machines are helping the humans annotate, and then it just becomes faster and more efficient as it keeps going. So it takes, with these big workloads for data annotation projects, it takes a workforce of annotators, and usually they're outsourced in another country where it could be a little bit more cost effective. So there's a couple ways to go about outsourcing that, and I'll tell you the difference. So there's BPO, which is business process outsourcing, versus crowdsourcing. So the core difference between the two is that the tasks in crowdsourcing come from various sources. Unlike outsourcing, where organizations rent functions from a specific outsourcing company, crowdsourcing can be done in various ways. This is mostly done on a digital platform or social networking sites. So but basically what it's saying there is when you're crowdsourcing annotators, you may not have as much quality control or even security as you would with if you go to an actual BPO provider that would allow for that kind of quality assurance and data security. So, and with some companies being kind of sensitive about their data and things like that, usually BPO is preferred, right? So these partnerships, by the way, with our business process outsourcing providers, helps us to bring jobs to underserved areas. As an example, our partnership with our BPO provider created jobs to support local Kenyan economies and has helped fight social inequalities by hiring women, young professionals, and people with disabilities. To give you an idea of how efficient and cost effective this makes data labeling, there was a security project that required 3 million data labels in just 4 months. Our partner, the workers working for our partner, produced 25,000 labels per day and saved the client 960 hours worth of data labeling. So now that we have kind of a solid understanding of data labeling, so what does data labeling look like looking ahead? The global data collection and labeling market size was valued at $1.67 billion in 2021 and is expected to expand at a compound annual growth rate of 25.1% from 2022 to 2030. The market is expected to witness a surge in the adoption of the technology owing to benefits such as extracting business insights from socially shared pictures and auto-organizing untagged photo collections. It also contributes to developing enhanced safety features in autonomous vehicles, such as condition monitoring, terrain detection, wear detection, and emergency vehicle detection. So you can see the graph, that doesn't apply to the global market, but it is for the Asia Pacific market. You can kind of see where video is in those bar graphs. It's this kind of a blue, the middle blue one, and video being the hardest to annotate and has the biggest demand today. You can see that it's showing the most growth compared to, let's say, audio or text, which I think text has been around for natural language processing has been around for some time now. So. This one is a hype cycle graph from Gartner. As you know, Gartner regularly puts out these graphs for different kind of industries or products. This one specifically is for artificial intelligence. So it shows you the hype cycle for AI, starting from the innovation of Trigger right at the beginning here, which is basically when the technology first hit the market. I'm not sure why it doesn't have the timeline there, but it's just showing you the different stages of technology and adoption. And the points represent some of the key developments and advancements happening throughout that journey. As you can see, data labeling is right here in the slope of enlightenment, right before the plateau, quote unquote, plateau of productivity, which is when typical businesses are more likely to benefit from it. I guess it becomes more of a prevalent technology at that point, a lot more common. And with that, I'd like to leave you with some funny machine learning memes that I found on the internet, starting with this. All right, last one. There you go. You saw that one before? Okay. And that concludes my presentation. Thank you. And I'll take some questions. If you have any, doesn't mean I'll answer them. I'm done. Go ahead.
I was curious about pictures that involve real photos, real data.
Yes.
How how you guys are looking into synthetic data. For example, a lot of copyright issues with, or the idea that where somebody can take an image, Photoshop it in a way where it's just a little bit enough to change the original, but
Right.
could be considered trademark or copyrighted. That's one way of making it synthetic, right?
Right.
And then with the advancements of imagery, synthetic imagery with like text to image, AI text to image, are you guys looking into those things in the future, or are you strictly sticking to real photos?
Well, as of right now, and I got to remind you, I just started working for Alegion like 3 or 4 months ago. So my technical knowledge and the data labeling is not that deep. As I said earlier, I just 3 months ago I couldn't spell AI, right? But with synthetic data, which we don't offer synthetic data. I think that's kind of our probably a competitive product compared to labeling actual videos and actual images. From my understanding, synthetic data, it doesn't duplicate like real life images or a real life set of data sets. So it may not account for like outliers and things as a real data set would, because you have an accurate representation of the images and videos that's out in the real world. So that's something I need to kind of learn more about, synthetic data. But I do understand that's actually, I think that's been around longer than data labeling. Let's go back to that slide. Yeah, it's right up here. Synthetic data is right in this kind of stage where back in the days, that's what companies were using to train their algorithms. And I guess now the preferred method, and it's more of a premium service, is getting actual, accurately labeled data, because it's expensive, is probably the way to go. As far as translating text into images, I don't work in the engineering department, so I know there's quite a bit, a few things that they're working on as far as patenting certain processes, and like the ones I described earlier, making the annotation activity or effort a lot more streamlined. So they're working on things like that. I haven't heard of text to image that they're working on that, but then again, I don't know everything that's happening in the engineering department for Alegion. So yeah.
Is there a target size for certain types of data that like they want to identify, I don't know, a dog? We need 1,000 pictures of a dog within 5 minutes. How many pictures of a dog?
That's another good technical question that I just don't know. Maybe he knows. But yeah, that's something I'd have to research. I don't know the kind of the sweet spot for how many data sets you need for the machine learning to actually start classifying dogs on its own. I don't know. Sorry.
Okay, so another question? Just to bring to another. Okay, so thank you so much.
Thanks.
Thank you so much.
Oh.
Asking is if you can stop the recording and make a new one, right?
Yeah.